Picture yourself standing at the rail of a ship, somewhere in the Indian Ocean, far from any coastline. It is the middle of the night. There is no moon, and yet you can see the water not sparkling, not flickering, glowing. The entire sea around you, in every direction, has turned the color of milk under starlight, a pale and even white that seems to come from beneath the surface itself. The horizon disappears. You cannot tell where the water ends and the sky begins. Your own hands, resting on the rail, would catch a faint light reflected up from the waves below. This is not a small patch of glowing water, the kind you might see stirred up by a paddle or a swimming fish. This is a sea that glows for hours, sometimes for days. Sailors have described crossing such water for an entire night and still finding it glowing at dawn, stretching to every edge of what they could see. Some reports describe glowing seas wide enough to cover an area the size of a small country. If you were standing there, the deck beneath your feet would feel like it was floating on light instead of water. From high above, looking down from a satellite in orbit, this same event looks like a pale bruise on the dark skin of the ocean, a soft glowing shape hundreds of kilometers across, visible for days at a time before it fades. No ship, no city, no storm, just the ocean itself, lit from within, spread out like a quiet secret the size of a small country, silent under the layer of clouds and dark that usually hides the sea at night. Before we go further, the planet has a new quiet wonder to share every night. If you'd like one waiting for you each evening, subscribe and let it come to you. The mystery at the center of this glow is a simple one to ask and a hard one to answer. We know, in general terms, that some of the light comes from tiny living things in the water, organisms so small you would need a microscope to see even one of them clearly. Each one can produce a small chemical light, a soft, cold glow with no heat, made through a chemical reaction inside its own body. That much is well understood. The trouble starts when you try to explain how billions of these tiny lights, spread across an area larger than some countries, could ever glow together at the same time for days on end without any storm or current holding them in place long enough to make that happen. A single glowing cell is easy to picture. A sea glowing edge to edge for 70 hours, as some ship logs have described, is much harder to explain. One idea is that vast blooms of light-producing bacteria grow across the surface layer of calm, nutrient-rich water, feeding and multiplying together until their combined light becomes visible even from space. Another idea points to slicks of decaying material, drifting mats of dead plankton or algae that pull bacteria in like magnets and hold them close enough together to glow as one. Both ideas have some support. Neither one fully explains how the light stays so even, so widespread, and so strangely steady for so long. If you sailed into one of these glowing patches tonight, you would feel very small and very quiet. The water would look solid, almost lit from a lamp hidden just beneath the surface. Your own wake, cut by the hull of the ship, might leave dark trails behind you instead of light ones, since the glow ahead can seem more constant than anything stirred up by motion. It is a strange kind of light. It comes from something alive, but it does not feel urgent or dangerous, or even fully understood by the people standing closest to it. Across the many long nights this documentary will spend with this question, we will look at old ship logs describing these glowing seas, centuries before anyone had a name for the tiny organisms responsible. We will look at satellite images that finally confirmed, only in recent decades, that sailors had not been imagining things. We will look at the ocean chemistry involved, the currents that may gather the right conditions in the right place, and the parts of the puzzle that remain stubbornly open. For now, it is enough to hold the image quietly in your mind. A ship gliding across water that glows like fallen snow under starlight, for reasons the people on board could feel, but never fully name. Picture yourself on the deck of a wooden ship 200 years ago. There is no engine hum, no electric light, only the creak of rope, the slap of sail, and the dark water sliding past the hull. Then, one night, the water stops being dark. It turns the color of milk or fresh snow under moonlight, and it stays that way for hours. This is not a story from a novel. It is a real event, written down again and again by real sailors, in real logbooks, across hundreds of years. The earliest clear accounts come from the age of sail, when ships crossed the Indian Ocean and the seas near Southeast Asia on long trading routes. A captain would note the date, the position of the ship, and then something like this. The sea appeared white as far as the eye could see. Sailors would lean over the rail and watch their own wake vanish into a field of pale light instead of black water. Some described it as sailing through a field of snow. Others compared it to clouds seen from above, except the clouds were beneath them, not above. What makes these reports strange is not just the light itself. Sailors already knew about glowing water. A ship's wake at night often sparkles, a soft blue-green shimmer that flares up when the water is disturbed by the hull or the oars. That kind of glow comes and goes with movement. It flickers where the water is stirred, then fades again into darkness within seconds. This event was different. The glow here did not need movement to appear. It did not flicker or fade. It simply sat on the surface of the sea, calm and steady, the way moonlight sits on a field of snow. Reports describe the glow lasting through an entire night, and sometimes returning again the next night, in the same stretch of water. Some accounts describe 2 or 3 nights in a row. A ship might sail for hours and never leave the pale water behind. Imagine driving through fog on a highway that never thins, mile after mile, except the fog is made of light instead of mist. That is closer to what these sailors described than any ordinary sparkle in a wake. For a long time, these reports sat in an odd position. They were written by trained officers, men whose job depended on accurate observation, yet the descriptions sounded almost too strange to believe. AC, they said, that glowed edge to edge, with no shore in sight and no lighthouse nearby, covering water so wide that the horizon itself seemed to disappear into the glow. Some scientists on land who read these reports later assumed the sailors were exaggerating or mistaking moonlight on clouds for something in the water itself. It was easy to imagine tired men at sea seeing something larger than it really was, but the reports kept coming from different ships, different captains, different decades, describing the same basic shape of event. A steady, wide, pale glow. No flicker, no clear edge, lasting, far longer than the brief sparkle everyone already understood. If it had happened once, it might have been a trick of the eye. Happening again and again, in similar regions of ocean, made it harder to dismiss. One idea that took hold early was simple. Something in the water was making the light, and it was spread very evenly and very widely. That idea sounds obvious now, but at the time it raised a harder question underneath it. What kind of living thing could cover an area larger than some countries and glow together at the same time for days without stopping? Competing ideas suggested the light might come from something non-living, some chemical reaction in the water, unrelated to any organism at all. Both ideas pointed to the same unanswered puzzle. How do you get a light this large, this steady, and this long-lasting, out of an ocean that should only sparkle for a moment and then go dark again? If you had stood at that rail, feet planted on damp wooden planks, the cold night air on your face, you would have felt the strangeness before you understood any of the science behind it. The sea beneath you would have looked like a floor of pale light instead of water, stretching out until it met a horizon you could not quite find. Your own shadow might have looked wrong, cast by light coming up from below instead of down from above. That basic experience, the pale glow filling the dark instead of a single flash and fade, is where every later question about the Milky Sea begins. Long before anyone had a name for the Milky Sea, there was simply the water and the light it sometimes carried. If you had stood on a fishing boat off the coast of Scotland 200 years ago, you might have heard a word passed quietly between the crew: Mareel. It meant the glow itself, the pale fire that clung to the wake of an oar, the shimmer that ran along a dropped net. The word came from an old Shetland dialect, rooted in Norse speech, carried across the North Atlantic by generations of fishermen. It did not explain the light. It simply gave people a way to talk about something they saw again and again but never fully understood. Mareel was small compared to what this episode is really about. It was the flash of light in a single wave, the brief sparkle stirred up by a moving hand or a startled fish. That kind of glow had a simple, almost comforting logic to it. Something touched the water, and the water answered with light. Fishermen learned to read it. A boat, leaving a bright trail, meant the water was full of something reactive, something alive and easily disturbed. This was the ocean's smallest performance, and it fit inside a single glance. But even in those early years, sailors spoke of something else, something the word Mareel could not quite hold. They described nights when the light did not need to be stirred at all. The whole sea simply shone, flat and steady, from the ship's hull to the edge of the dark horizon. No oar had to touch it. No fish had to dart through it. It was already glowing before anyone arrived, and it kept glowing long after they had passed. If you had stood at the rail on one of those nights, you would have felt the strange stillness of watching light that asked nothing of you at all. This is where the true mystery of this episode begins to take its shape. The small, familiar sparkle of Mareel came from tiny organisms disturbed by motion, plankton and small crustaceans that flash when jostled by a current or an oar. That mechanism, while still wondrous, at least made a kind of sense. Motion caused light, but the sustained glow, the kind that could stretch for days across open water, did not follow that pattern. It did not flicker with disturbance. It sat on the surface of the sea like something already burning, and it stayed lit whether the water moved or not. Early naturalists tried to fit this larger glow into the same explanation as Mareel, only bigger. One idea was that the sustained glow was simply an enormous, unusually dense cloud of the same small organisms responsible for the little sparkles fishermen already knew. If a single wave full of plankton could flash, perhaps a wave large enough, packed tightly enough, could glow without needing to be touched at all. This idea had a comforting simplicity. It suggested a difference of scale rather than a difference of kind. But other observers were not convinced. They noticed something the flash organisms could not explain. The great glowing patches did not flicker or fade with the rhythm of waves. They held a flat, continuous light, more like a lit pane of frosted glass than a field of individual sparks. Whatever produced this glow appeared to shine constantly, not in response to touch, but on its own terms, hour after hour. That distinction, quiet and easy to miss, planted a seed of doubt that would take more than a century to properly investigate. If you had been the one to first notice this difference, you might have felt a small chill of recognition, the sense that the sea was doing something categorically different from what your grandfather's word for it described. Mareel was disturbance, turned briefly luminous. This other glow felt like the ocean, holding a light of its own, something closer to a slow, patient burning than a startled flash. For a long time, no one had the tools to test which idea was closer to the truth. Sailors wrote down what they saw because it was rare and beautiful, not because they expected an answer soon. The word Mareel stayed useful for the everyday sparkle in a boat's wake, but it never stretched to cover the vast, level fields of light some ships crossed for 2 or 3 nights running. That gap between a word for a small wonder and an unnamed wonder far larger is where our story actually starts. The light had already existed for longer than anyone had watched it. The naming came late, and the true explanation, even now, has not fully arrived. Picture yourself standing on the deck of an old wooden ship, somewhere far from any coastline. Below you, the water is not dark. It glows a soft, even silver, as if the sea has swallowed the moon and is letting the light leak back out through its skin. You would feel the deck sway gently under your feet, the same as any other night at sea. But the water around the hull would look nothing like water should. To understand what made that glow, we have to start small, very small. The light did not come from the ocean itself, and it did not come from any mineral in the water. It came from living things, tiny beyond what the human eye can see without help. Bioluminescent bacteria are the leading suspect behind the Mareel we spoke of earlier. Single-celled organisms so small that millions could fit inside a drop of seawater, resting on your fingertip. Each one carries a set of chemical tools that let it produce light through a reaction called bioluminescence, a process where a molecule called luciferin reacts with oxygen and an enzyme called luciferase to release a small, cool flash of light. That reaction does not make heat the way a candle or a lantern does. It makes light the way a firefly makes light, through pure chemistry, no flame involved at all. If you cupped your hands in glowing water and lifted them to your face, the light would feel like nothing. No warmth, no burn, just a pale glow resting in your palms, cool as the water itself. The chemistry inside a single bacterium is well understood. Scientists have studied luciferin and luciferase in laboratories for decades, and the reaction itself is not the mystery. The mystery is what happens when you multiply that single dim light by billions, then by trillions, then by numbers so large they stop feeling like numbers at all. One glowing bacterium is a curiosity, a sea full of them, stretched across an area larger than some countries, is something else entirely. The question of how that jump happens from one candle-sized flicker to a light bright enough to see from space remains only partly answered. Some researchers believe the bacteria cluster around tiny floating particles of organic matter, bits of dead plankton, or drifting cellular debris, feeding on them and multiplying in place. This would explain why the light seems to hang in patches rather than moving with the current, like a school of fish. Other researchers point to algae, tiny plant-like organisms that sometimes host these bacteria on their surface, carrying them along like passengers on a raft. Both ideas are supported by some evidence. Neither one fully explains how the light stays even and unbroken across such enormous stretches of open water. There is something quietly strange in knowing that the ocean's glow depends on chemistry borrowed from the same family of reactions found in fireflies blinking over a summer field, or in certain mushrooms that glow faintly on a forest floor at night. Life on Earth, in very different corners of it, seems to have discovered the same trick more than once. The ocean did not invent bioluminescence. It simply has more room for it, more water, more darkness, more places for that cool light to spread. The water itself carries no special ingredient that causes this. Seawater is mostly the same everywhere. Salts of sodium and chlorine, dissolved in a molecule of hydrogen and oxygen. Water that likely arrived on Earth billions of years ago, carried by ice and comets from the outer edges of the solar system. What makes one patch of ocean glow and another stay dark is not the water. It is what lives in it, and why those living things suddenly act together is the piece no one has fully pinned down. If you sailed through a glowing patch tonight, the water sliding past the hull would carry no scent of anything burning, no warmth rising from below. It would simply glow, quietly, as if lit from some source deep beneath the keel. You might reach over the rail and let your fingers trail through it, watching pale light curl and eddy around your hand, before smoothing back into stillness. The chemistry is simple. The coordination behind it is not, and that gap between the small and the vast is where the real question still lives, waiting patiently in the dark water below every ship that has ever crossed it. Picture yourself bent over a small wooden desk, a lantern swinging gently above you, ink drying slow in the damp night air. This is where the story of the glowing sea really lives, in the careful, cramped handwriting of ship's officers who had a duty to record what the ocean did each night. Their logbooks were not written for wonder. They were written for navigation, for weather, for the safety of the crew, and yet, again and again, across centuries and oceans, the same strange entry appears. The sea, they wrote, had turned white, not sparkling, not flashing, white, like snow, like milk, like the underside of a cloud. If you read enough of these entries side by side, a pattern starts to form. Captains describe the light as covering the horizon on every side, with no clear edge and no clear course. Some noted the ship seemed to sail through cloud instead of water. Others wrote that the light stayed the same whether the sea was calm or rough, which puzzled them because so many ocean lights come and go with the motion of waves. That steadiness is one of the forces at the center of this mystery. Wind and current can drive water, stir it, push it into swells and foam. But a glow that holds its shape and its shine through changing weather suggests something else is doing the work. One force worth thinking about is turbulence, the churning and mixing that happens when currents run against each other, or when wind drags across the surface for days without a break. Turbulence can stir tiny organisms up from deeper, darker water into the surface layer where sunlight and oxygen behave differently. Some researchers believe this kind of physical mixing may set the stage for a bloom of light-making life, even if it does not fully explain why the light spreads so evenly, or why it lasts so long. A storm can start a fire. It does not always explain why the fire keeps burning for days after the wind dies down. Heat is another quiet force in this story. Warm surface water, layered over cooler water below, can trap nutrients near the top, feeding whatever tiny life is already there. In some parts of the ocean, this warm layer stays remarkably still for long stretches, almost like a lid. If a light-producing bloom forms under that lid, It may stay in place far longer than a bloom exposed to rougher, colder water. This is one reason certain regions of ocean report milky seas again and again, while most of the world's water almost never does. The heat does not create the glow by itself. It simply builds a room where the glow can stay lit. Pressure plays a smaller, stranger role. Out on the open ocean, water pressure at the surface is gentle. Nothing like the crushing weight found in the deep. That even slight differences in pressure, caused by shifting winds or the pull of tides, can nudge water masses to slide over or under each other. Picture two sheets of glass, one warm and one cool, gliding past one another in the dark. Where they meet, tiny organisms can gather, trapped at the boundary like dust caught between panes. Some scientists wonder if these boundaries, called fronts, act like invisible fences that hold a glowing bloom together instead of letting it scatter across hundreds of kilometers of open water. None of these forces, on their own, fully explain what sailors described. Turbulence explains mixing, not duration. Warm layers explain stillness, not the reason the light appears at all. Pressure fronts explain boundaries, not the coordination that would let so much water glow at once, as if lit from a single switch. This is where the mystery stays open. The physical ocean can shape where a glow happens and how long it might survive. It cannot yet explain why the living things inside that water choose or are driven to shine together across such enormous distances. If you stood at the rail of one of those old wooden ships, none of this science would have been available to you. You would only feel the slow roar of the deck beneath your boots, the salt air on your skin, and the strange, steady light rising off water that should have been black. The forces moving beneath your feet, heat and pressure, and the invisible drag of currents would have been shaping that light in ways no one on board could measure. Even now, with satellites and sensors and centuries of collected logs, those same forces are only partly understood. The old sailors simply wrote down what they saw and trusted someone, someday, might explain it. Picture yourself standing at the rail of a small boat on a warm night, watching your own wake. As the boat cuts through the water, you see flashes of blue-green light trailing behind you, then fading. This is sparkle. It comes and goes with your movement. Each flash is a single creature, or a small cluster of them, reacting to the push of water against its body. It is beautiful, but it is local. It belongs to you and your boat, and nowhere else. Now imagine that same boat sailing for 6 hours, and the whole time the water around you does not flash. It glows, not just behind the boat, but ahead of it, beside it, and as far as your eye can see in every direction. There is no dark water bordering the light. There is no edge to swim toward. This is the difference the old sailors were trying to describe when their logs stopped talking about sparks and started talking about milk, or snow, or a field of pale fire lying flat on the sea. The gap between these two things is not small. A single flash of sparkle might last less than a second and cover a patch of water smaller than a dinner plate. A Milky Sea, by contrast, can spread across an area larger than some countries. One event recorded in the northwestern Indian Ocean was later estimated, using satellite images, to cover about 100,000 square kilometers. That is roughly the size of Kentucky, glowing softly from below, all at once, for days. Think about what that means in terms of individual creatures. The light in both sparkle and glow comes mostly from bioluminescent bacteria, organisms too small to see without a microscope. A single one of these bacteria is a few thousandths of a millimeter long. You could line up a few hundred of them across the width of a human hair. For a stretch of ocean the size of Kentucky to glow evenly, you are talking about a number of these bacteria that is difficult to say out loud in a way that means anything. Trillions upon trillions spread through the surface layers of the sea, all producing light at close to the same time. Here is a way to feel the scale rather than just hear it. If you shrank one glowing bacterium down to the size of a grain of sand, and you tried to fill an area the size of a large lake with that sand 1 grain deep, you still would not have enough grains to match the real numbers involved in a single Milky Sea event. The ocean does not do this occasionally in a scattered way. When it happens in staggering amounts, gathered into one contiguous space. And there is the matter of time. Sparkle from disturbed bacteria dies out in less than a second because the light comes from a short chemical reaction tied to a physical bump or nudge. A Milky Sea does not fade in a second. Some events have lasted for a single night. Others, according to historical accounts and at least one satellite record, appear to have lasted for several nights in a row, with the ship's crew watching the same pale glow morning after morning as they crossed it. One theory holds that a bacterial bloom, once it reaches high enough density in the water, can sustain a slow, steady kind of light rather than a flash, and that this steady glow can persist for as long as the bloom itself holds together. A competing idea suggests that what sailors are seeing across multiple nights may sometimes be different patches of the same broader bloom drifting past the ship rather than one unbroken sheet of light staying in place. Which explanation fits which historical account remains unresolved, because most of these events happened long before anyone could measure them properly. If you were floating in the middle of one of these events, none of the numbers would matter to your body. You would only feel the strangeness of it. The horizon would disappear into the glow. The sky above might be black and starry, while the sea below looked like a soft, endless field of light, with no dividing line between water and air. Your hands, resting on the rail, would not tell you whether you were looking at something small and simple, repeated an unimaginable number of times, or something the ocean does as one connected act. Both descriptions are true, and neither one fully explains what makes trillions of tiny lives glow together instead of alone. That gap between the size of one bacterium and the size of a glowing sea sits at the center of the mystery, and it is still open. If you could lean over the rail and cup a handful of that glowing water, you would find nothing solid at all. No lantern, no glass, no floating creature you could hold between two fingers. Just water, faintly warm from the day's sun, running clear through your hand in the dark. The light would seem to come from nowhere and everywhere at once, soaked into the sea itself like something dissolved, rather than something placed there. The truth is smaller than anyone expects. Most ocean light of this kind comes from single-celled organisms so small that 1,000 of them could fit inside a grain of sand. Some are a kind of plankton called dinoflagellates, tiny drifting cells that flash when the water around them moves. Others are bacteria, simpler still, with no moving parts at all, glowing not in flashes, but in a low, steady, continuous shine. This second kind, many researchers believe, is the one responsible for the sustained glow sailors have described for centuries, the kind that does not sparkle and fade, but sits on the water like pale milk for days at a stretch. Each one of these bacteria is far too small to see with the eye alone. You would need a microscope to find a single glowing cell, a rod-shaped speck adrift in a drop of seawater. And yet, somehow, when enough of them gather, The ocean itself seems to catch fire with cold light, visible for miles, visible in some cases from space. That gap between one invisible cell and a glowing sea the size of a small country is where the real mystery lives. No one has fully explained how a population that small could coordinate itself across such a distance, or why it would glow steadily rather than in the quick flashes typical of disturbed plankton. One leading idea points to the bacteria's relationship with tiny floating algae. Some researchers believe the glowing bacteria live attached to these algae in vast numbers, riding along as the algae bloom and multiply across the surface of the sea. If the algae spread wide enough, carried by currents and nutrients rising from below, the bacteria attached to them could in theory light up an area far larger than any single colony could manage alone. It is a tidy explanation, and it fits some of what satellites have recorded, but it does not fully explain why the light stays on for so long, glowing through nights and into days, when most bioluminescent blooms fade within hours. A competing idea suggests the bacteria are not simply riding along, but multiplying on their own, feeding on decaying material at the surface, spreading through some process not yet fully mapped. Under this view, the size and duration of the glow would depend less on any host organism and more on the exact chemistry of the water in that stretch of ocean. Both ideas remain open. Neither one, on its own, accounts for everything sailors have reported. What is agreed upon is the strange nature of the light itself. It is called cold light because, unlike a candle or a lantern, it produces almost no heat. The chemical reaction inside each bacterial cell converts energy directly into a soft blue-white glow, wasting almost nothing as warmth. If you held that glowing water in your hand, it would feel no different from any other seawater. The light would seem to have no source you could touch, no fire you could feel, only that pale luminous color spreading across your skin. Under a wide open sky, with the moon down and the stars sharp overhead, the surface glow can erase the line between water and horizon entirely. Ships crossing these patches sometimes reported a sensation of drifting through a lit fog, the sea and sky merging into one soft field of light. The water would still move beneath the hull, the way any water moves, rising and falling with the same rhythm, but the color would be wrong, pale and constant, without the black depth the ocean usually holds at night. Scientists studying seawater samples from these events have confirmed the presence of glowing bacteria in astonishing numbers, sometimes tens of thousands per milliliter. That confirms the light comes from life, not chemistry alone, and not reflection of any outside source, but confirming what produces the glow is different from explaining how it organizes itself across hundreds of kilometers, or why some patches of ocean seem primed for it, while most of the sea never glows at all. If you drifted above that surface tonight, you would see something that looks organized, deliberate, almost patterned, and you would be looking at billions of separate lives, each one blind, each one simple, each one somehow part of a glow far larger than itself. If you could scoop a handful of that glowing water and hold it close, you would see almost nothing at first, just water, cool and clear, running through your fingers in the dark. The light would seem to hide from you the moment you tried to look directly at it. This is one of the strange truths about the glow. It often responds to disturbance, then fades again, as if it prefers to be left alone. The light itself comes from a chemical reaction, not from anything burning or electric inside. Certain bacteria, a molecule called luciferin, reacts with oxygen, aided by an enzyme called luciferase. That reaction releases energy as light instead of heat. This is called bioluminescence, which simply means light made by a living thing. It is the same basic kind of chemistry that makes a firefly blink in a summer field, though the ocean version comes from cells far too small to see alone. A single bacterium glowing this way produces a point of light so faint that no human eye could ever catch it. It would take many thousands of these cells packed into a small space of water just to produce a glimmer bright enough to notice. And yet sailors have described glows that stretch past the horizon in every direction, lasting through entire nights, sometimes for several days in a row. The gap between one glowing cell and an entire glowing sea is where the real puzzle begins. No one has fully explained how so many individual points of light manage to appear together at the same brightness over such a wide stretch of open water. One idea centers on the bacteria themselves and how they seem to switch their light on and off together rather than randomly. Some species use a process called quorum sensing, where each cell releases a small chemical signal into the water around it. When the concentration of that signal crosses a certain threshold, meaning enough bacteria are packed close enough together, the whole group begins to glow at once. If you imagine a room full of people who all decide to hum quietly, only once enough voices join in, you have something close to the idea. It explains coordination among cells that are near each other. It does not fully explain how that coordination might hold steady across kilometers of shifting, mixing seawater. A competing idea looks less at the bacteria's internal signaling and more at the surrounding environment, shaping them from outside. Warm surface layers, certain salt levels, and slow-moving currents may create conditions where dense bacterial populations simply form on their own, or switching to their glowing state for similar chemical reasons at similar times. Under this view, the light is less like a coordinated performance and more like thousands of separate fires catching under nearly identical weather. Researchers who study these blooms are still weighing how much of the glow comes from true signaling between cells and how much comes from shared conditions acting on cells that never truly speak to each other at all. If you stood at the rail of a ship passing through a glow like this, the water below you would look less like the sea and more like a pale sheet of light stretched flat to the horizon. Your eyes would search for a source, a single glowing patch to explain the rest, and find none. The light would simply exist everywhere at once, the same shade of pale blue-white in every direction you turned. It is easy to understand why old sailors reached for words like milk or fire when trying to describe something with no visible center. Some researchers have wondered whether the bacteria live inside larger organisms first, perhaps within algae or tiny drifting animals, and only release their glow once those hosts die or break apart. This would mean the true trigger for a Milky Sea has less to do with bacteria multiplying on their own and more to do with a larger die-off, feeding them all at once. It remains one possibility among several, tested against limited samples pulled from ships lucky enough to pass through a glow while carrying the right equipment. What stays constant across every theory is the strangeness of the scale. A chemical reaction built for a single microscopic cell somehow produces a light large enough to be seen from space. The mechanism at the smallest level is understood well enough in a laboratory dish. The mechanism at the level of an entire glowing sea, holding its light steady for days, still resists any full explanation. If you crossed that water tonight, the glow beneath your ship would carry the same quiet, unclaimed light it carried for sailors centuries ago. Picture a single bacterium small enough that 1,000 of them could rest on the head of a pin. On its own, it is nothing you could see. Its light, if you could isolate it, would be a pinprick too faint to matter. And yet somehow, across hundreds of kilometers of open sea, enough of these bacteria light up together to turn the ocean into a glowing plain, visible from space. That gap between one small cell and a light that satellites can track is still not fully explained. If you tried to imagine the number of cells required, you would run out of ways to picture it. The species most often blamed for this glow is called Vibrio havii, a bacterium that lives in seawater and on the surfaces of small drifting organisms. It carries genes that let it produce light through a chemical reaction, one that needs oxygen and a molecule called luciferin, paired with an enzyme called luciferase. Mix them together in the right conditions and the reaction gives off a soft blue-white glow. This is not fire. It makes almost no heat. It is closer to a cold chemical hum that never needs to be relit. What makes this light strange is that a single bacterium usually does not bother to glow. Below a certain population size, most of these cells stay dark, saving their energy. Researchers have found that they seem to sense how many neighbors are nearby through a process called quorum sensing, where they release and detect small molecules that build up as the population grows. Only when the crowd reaches a certain density do enough of them switch on their light at once. It is less like a single decision and more like a threshold being crossed by trillions of cells in the same rough window of time. If you stood on a deck above one of these blooms, you would have no way of knowing that trillions of tiny chemical clocks had just crossed the same line together. You would only see the result: water that looks lit from underneath, calm and pale, stretching farther than your eyes can measure. The mechanism behind the glow of one cell is well understood in laboratories. The mechanism behind an entire sea crossing that threshold together over an area larger than some countries is not. One idea is that the bacteria are not really coordinating across the whole area at all. Instead, they may simply be living inside a huge patch of algae, the tiny drifting plants that bloom in vast mats when the water is warm and full of nutrients. If those algae already cover hundreds of kilometers, the bacteria living inside that mat would only need to respond to their own local neighbors. The huge glow would then be less like one signal and more like many small signals, each following the same rule, spread across a surface large enough to look unified from above. A competing view focuses on the water itself rather than the algae. Some researchers wonder if certain currents create conditions calm and stable enough to let one continuous bacterial layer stretch and thicken over days, moving as a single body rather than many separate patches. Under this idea, the glow would behave more like weather, spreading and drifting as one system rather than many copies acting in parallel. Both explanations remain open, since ships passing through a Milky Sea rarely have the equipment to sample water across its entire width at once. What is clear is that the glow does not last forever, and it does not follow a fixed calendar. A Milky Sea might last for 2 nights or for more than a week, then fade the way it began, quietly and without warning. Some researchers compare this rise and fall to the pulse of the tides or the turning of the seasons, a rhythm built into something living rather than something mechanical. Others resist that comparison. Since tides return on a schedule you can set a clock by, while these blooms seem to obey rules we have not yet mapped. If you sailed through the same water a month later, the light would likely be gone. The surface returned to ordinary black. Nothing on the surface would tell you a glow had ever been there. The bacteria that made it would still exist, scattered and dim, waiting for their numbers to build again, somewhere else, on some future night no one can predict. The rhythm is real, but its calendar remains unwritten, hidden inside water that keeps its own private time. Picture the deck of a ship at night, somewhere off the coast of East Africa, or in the waters near Indonesia. You lean over the rail, and the sea does not look like the sea anymore. It looks like a field of pale snow, stretching to a horizon you cannot find. If you knelt down and touched the water, it would feel no different than any other ocean, cool, salt-heavy, moving with the slow breath of a swell. And yet it glows. What makes this stranger is scale. A single glowing wave, a trail of light kicked up by a dolphin's fin. That is one thing. Sailors have seen that, for as long as there have been sailors. But the Milky Seas that this episode follows are something else entirely. They can stretch across 40,000 square kilometers of open ocean, an area larger than Switzerland, glowing steadily for 2 or 3 nights in a row. The light does not flicker with each wave. It sits there, calm and even, like the sea has been lit from underneath by something patient. To understand why this matters, it helps to think about what usually causes ocean light. Most bioluminescence, light made by living things, comes from creatures reacting to disturbance. A fish swims by, and the water flashes where its body pushes through. A boat's wake churns up light for a few seconds behind the hull. That kind of glow is a response, a burst tied to movement. It fades as soon as the water goes still again. The Milky Sea does not behave that way at all. It seems to glow whether anything disturbs it or not, as though the disturbance is beside the point. One leading idea points to a type of bacteria called Vibrio havii, a bacteria, a single-celled organism, too small to see without a microscope, capable of producing its own light through a chemical process called bioluminescence. On its own, one bacterium gives off a light so faint no human eye could ever catch it. But researchers who have studied water samples from Milky Sea events have found staggering numbers of these bacteria clustered together, sometimes attached to the surface of tiny drifting algae. In large enough concentrations, their combined light could, in theory, add up to something visible from a ship's deck, or even from space. That still leaves an unanswered question: what convinces billions of individual bacteria across such a wide area to glow in a coordinated way, rather than as scattered, random flickers? This is where the idea of neighbors becomes useful, because a Milky Sea does not exist in isolation. It borders on entire food systems. Some researchers wonder whether the bacteria are riding on blooms of phytoplankton, the tiny drifting plants that form the base of the ocean's food chain. Where the phytoplankton spread, the bacteria might spread with them, using the algae as tiny rafts. Under this view, the Milky Sea is less like a single glowing organism and more like a sprawling neighborhood, one population's growth pulling another population along with it, both lit and unlit parts of the ocean pressed right up against each other. A competing view looks less at biology and more at ocean physics. Certain regions of open water, parts of the Arabian Sea, waters near the Java coast, patches of the Indian Ocean, see Milky Sea reports again and again, far more than anywhere else. Some scientists suspect this has to do with currents and nutrient upwelling, the slow rise of nutrient-rich deep water toward the surface in specific zones. Where the ocean's neighboring layers mix in just the right way, conditions might exist for a glow to gather and hold. That would mean the sea does not glow anywhere by chance. It glows at address, in coordinates the ocean itself seems to prefer, for reasons still not fully mapped. Neither explanation accounts for everything sailors have described. The bacterial idea does not fully explain how the glow can stay so even and so calm across such enormous distances. The physical idea does not fully explain why some years bring several Milky Sea events and other years bring none at all. What is clear is that the phenomenon does not stand apart from the rest of the ocean. It borders on algae blooms, on nutrient cycles, on currents that shift with the seasons, on food chains that reach from the smallest bacterium up through fish and seabirds, and whatever satellite happens to be passing overhead at the right hour. If you crossed one of these events at night, you would feel very small and very quiet, the water glowing on every side of you like a sea has decided to hold still and shine. You would not be able to see where the glow ends. Neither, most nights, can the instruments built to measure it. Picture yourself far above the ocean, higher than any bird could fly, in the dark quiet of low orbit. From up there, the night side of the earth is mostly black, with only a few scattered lights below, small clusters where cities glow along coastlines. Then, in the middle of nothing, over open water with no islands and no ships in sight, a satellite camera has sometimes caught a pale patch of light lying flat and even across the sea. It looks almost like a cloud lit from underneath, except there is no cloud there at all. These images come from a satellite that was never built to find glowing water. It carries a low-light sensor meant to track clouds and storms at night, using the faint light of the moon to see shapes in the dark. Almost by accident, researchers found that this same sensor could pick up something else entirely, a soft, milky brightness sitting on the ocean's surface, sometimes larger than a small country. If you were floating above that patch in a boat, you would see nothing but flat white light stretching to every edge of the horizon. The scale of these glowing patches is one of the strangest parts of this mystery. Some recorded Milky Seas have covered more than 100,000 square kilometers, an area larger than some entire nations, glowing at a steady low light, for days or even weeks at a stretch. A single firefly can light up for a few seconds. A jellyfish drifting past a diver might flash for less than that. But this is a light that does not flicker or fade with the waves. It simply stays on, spread across a stretch of ocean too large to cross by ship in a single night. One widely discussed case came from a ship's log in the year 1995, describing a sea that glowed steadily for hours as the vessel moved through it near the coast of Somalia. Decades later, researchers went back and matched the ship's location and date against satellite records from that same stretch of ocean. They found a bright patch in the images, sitting in almost the same place the sailors had described. It was one of the first times an old written account and a satellite record lined up so closely, turning a strange story into something closer to a measured event. Even with that match, the satellite images raise their own kind of open question. The sensor can show that a patch of ocean is glowing and roughly how large it is, but it cannot say for certain what is happening in the water underneath. Researchers still rely on theories built from smaller studies of bioluminescent bacteria, the kind of single-celled organisms that can produce a cold chemical light when they gather in enormous numbers. One idea is that certain bacteria bloom across the surface in sheets thin enough and steady enough to register from space, all lit at once by some shared biological signal that scientists do not fully understand. A competing idea points to the water itself, wondering whether calm currents and gentle mixing might spread already glowing organisms into unusually even, wide layers, rather than the bacteria producing some unified group behavior at all. The rarity of these events adds another layer to the puzzle. Ships report ordinary bioluminescence fairly often. The familiar sparkle of light, stirred up by a moving hull or a breaking wave. Milky seas, by contrast, appear only a handful of times most years in the entire satellite record, and only in certain parts of the world's oceans. If you sailed through one of the more common sparkling waters, the light would flash and vanish around you, gone in an instant. A Milky Sea, by contrast, would hold steady around your ship for hour after hour, as if the water had simply decided to stay lit. No one has yet caught one of these patches with instruments in the water at the same moment a satellite photographed it from above. Ships that stumble into a Milky Sea rarely carry the right equipment, and research vessels sent to study bioluminescence rarely happen to be in the right place at the right time. That gap leaves scientists working from two different kinds of evidence that have almost never overlapped, one from orbit and one from the deck of a passing ship. Until those two views line up more often, the true cause of a light this large, this steady and this rare, will stay just out of reach, glowing somewhere below the clouds, while the cameras above keep watching. If you leaned over the rail with a light meter in your hand, you would find something strange. The glow does not have a sharp edge you can point to and say, "This is where it starts." It fades in so slowly that your instrument struggles to tell you when the dark water ends and the glowing water begins. This is one of the quiet puzzles of a Milky Sea. Scientists who study bioluminescence, light made by living things, usually work with small bright points, a single flash from a startled organism, a streak behind a swimming fish. These are easy to measure because they have a clear beginning and a clear end. A Milky Sea offers no such gift. It is not a flash, it is a field, spread evenly, dim and constant, covering the water the way frost covers a window. To measure something with no edges, researchers have had to borrow tools built for other purposes. Some have used the same low-light sensors designed to study faint starlight through clouds. Others have turned to satellites meant to track city lights or wildfire smoke, adjusting their instruments to catch a glow far dimmer than any electric bulb. Even with this borrowed equipment, the readings from a Milky Sea often sit right at the edge of what the sensors can detect. You are, in effect, trying to measure a whisper with a microphone built for shouting. The light itself, when studied closely, has its own quiet texture. It is not perfectly steady. Under magnification, some samples of glowing water show faint pulses, small rises and falls in brightness that repeat every few seconds. No one has fully explained why. One idea is that these pulses come from the biology of the bacteria themselves, tied to some internal rhythm of feeding or dividing. Another idea is that the pulses are simply the water moving, carrying slightly denser patches of glowing cells past the sensor and then away again. Both explanations remain open, and neither has been ruled out. There is also the color of the glow to consider. Most Milky Seas produce a pale blue-white light, similar to moonlight on frost, but careful measurements have found tiny shifts in that color, from one glowing patch to another, shifts too small for your eye to notice, but visible to a spectrometer, an instrument that splits light into its exact wavelengths. Some researchers wonder if these small color differences point to different bacteria species doing the glowing, or different mixes of species working together. Others think the shifts might come from the water itself, filtering the light as it passes through different depths of plankton and sediment. If you skimmed a cupped hand through the water during a milky sea, the light clinging to your skin would look plain and simple. The instruments say otherwise. Scale brings its own quiet wonder. A single glowing bacterium is smaller than the width of a human hair, invisible without a microscope. Yet, when billions of them gather in the right density, they produce a light bright enough to read a ship's compass by, without any other lamp lit. The gap between the tiny cell and the vast glowing field is one of the details that makes this mystery worth sitting with. No one organism decides to make a sea glow. The glow simply happens once enough of them are present, once the water holds them close enough together for long enough. Measuring exactly how many cells it takes and how close they must be has proven difficult. Laboratory cultures of the same bacteria can be grown at high density without producing anything like the light of an open ocean bloom. This gap between the lab and the sea is still not understood. Some researchers think there is a difference in oxygen, temperature, or some chemical signal the bacteria only receive in open water. Others suspect the lab simply cannot recreate the exact conditions of a real bloom, no matter how carefully it tries. If you floated quietly on the surface of a milky sea, none of this complexity would announce itself. You would only see calm, pale water stretching to the horizon and feel the strange hush that light without shadow seems to bring. The instruments below the surface and far above it in orbit would be recording numbers that still puzzle the people who study them. Small details, patiently gathered, without a full answer yet. The glow keeps its edges soft, and for now, so does our understanding of it. Picture yourself leaning on a ship's rail at 2 a.m, watching the same pale light spread across the water for the 3rd night in a row. Most bioluminescent sparkle burns out fast. A wave breaks, a fish darts through the dark, and the flash lasts a second before it fades. But sailors have reported something else entirely. They have described a low, steady glow that does not flicker or fade. It simply stays, night after night, as if someone left a lamp burning under the sea and forgot to turn it off. The earliest written accounts of this steady glow go back centuries, tucked into ship logs and captains' journals. A vessel would cross into a patch of milky water, and the light would still be there the next night, and the night after that. Some logs described glowing seas lasting 2 or 3 days. A few described them lasting longer. For a long time, these reports sat in old paper archives, treated the way sailors' tales often are, as color for a story rather than data for a scientist. The trouble was scale. A single glowing bacterium lasts only as long as its own chemical reaction. A flicker measured in fractions of a second. A glow that holds steady for days across open water asks a very different question. One early researchers had no easy way to answer. The chemistry itself was understood well before anyone connected it to a multi-day event at sea. Certain bacteria carry an enzyme called luciferase, which reacts with a molecule called luciferin to release energy as light instead of heat. This is the same basic process fireflies use, just built by a different kind of life. Under a microscope, a lone glowing bacterium is unremarkable. One point of cold blue light among trillions of dark cells. The mystery was never the chemistry of a single organism. It was how that chemistry could stay switched on, in step, across a stretch of ocean big enough that a ship might sail through it for a full day and never reach the far edge. One early theory held that these reports were simply exaggerated, memory sharpened by boredom and dark water. the same way a long watch can turn a shadow into a shape. This idea held for a long time, partly because there was no instrument capable of checking a claim made in the middle of the ocean, far from any coastline, in an era before satellites. A ship's log could describe the glow, but it could not measure it, and a lone eyewitness account is a fragile thing to build a theory on. Your own eyes, doing the same work at the same rail, might have doubted what you were seeing too. The turn came slowly, not with a single dramatic discovery, but with a pattern that kept repeating across unrelated ships, unrelated decades, unrelated oceans. Different crews, with no way to compare notes, described the same thing. A flat, even light with no dark patches, stretching farther than a lantern could show. That consistency became its own kind of evidence. If confusion or exaggeration were the whole explanation, the details should have drifted apart over time and distance. Instead, they lined up. Confirmation eventually came from above rather than from the deck of any ship. Satellites carrying low-light sensors, built originally to track faint clouds and city lights at night, began picking up pale patches on the open ocean that matched the coordinates and rough timing of old ship reports. One glowing patch recorded from orbit was estimated to cover an area larger than some small countries, and it held its light for several nights running before fading from view. That single image did more to settle the question of duration than a century of first-hand logs had managed on their own. What the satellite images could not do was explain the coordination. Seeing the glow from space confirmed its size and its persistence, but not its mechanism. How do bacteria spread across so much water manage to glow in a way that reads as one continuous sheet of light, rather than countless separate flickers, sustained for days at a stretch? Some researchers propose the bacteria cluster on drifting algae in numbers dense enough to hold a steady output. Others wonder if a slower, larger die-off releases nutrients that keep local blooms lit far longer than a normal life cycle allows. Neither idea fully accounts for the evenness sailors describe, that flat horizon-to-horizon light, with no seam in it. The history of this discovery is really a history of patience, of old paper claims outlasting doubt, until a machine in orbit happened to look down at the right moment. It confirmed that the glow is real, that it lasts, that it is large. It did not confirm why. If you had been standing at that rail across all those decades of disbelief, the water beneath you would have looked exactly the same the whole time, pale and quiet, keeping its answer to itself. If you looked down at a milky sea from above, you might expect it to look ragged, like a cloud pulled apart by the wind. It does not. Milky seas often hold a shape that seems almost drawn on purpose, with edges that stay smooth for a long time. This is one of the strange parts of the mystery. A glow made by billions of separate drifting bacteria should smear and scatter. Instead, it often keeps its form for days. Wind moves the surface of the ocean all the time. It pushes small waves into bigger ones, and it drags warm water into cold water, mixing everything it touches. You would think a strong wind might tear a glowing patch apart within hours. Some milky seas do fade and fray at their borders, thinning where the wind works hardest, but other glows have been reported holding their basic outline through a full night of weather that should have scattered them. Sailors have described sailing along the edge of a glow for hours, watching it stay just as sharp as when they first saw it. Currents complicate the picture even more. Ocean currents are not simple rivers moving in one straight line. They twist, they loop, they slow down in some places and speed up in others. A drifting patch of bioluminescent bacteria, those tiny living things that make their own cold light, should get pulled into these twists and pulled apart. Some researchers think slow-moving currents near the surface may actually help hold a glow together for a while, moving the whole patch as one body instead of shredding it. Others think the shape we see may not be the bacteria moving as a group at all, but the visible outline of a much larger patch of nutrients or algae sitting just below the surface, feeding the glow evenly across a wide area. Under this idea, the light is less like a marching crowd and more like a lit-up floor beneath still water. Both explanations remain open. Neither one has been shown clearly enough to close the question. If you crossed one of these glowing fields at night, you would notice something else that seems to argue against a simple explanation. The light often does not brighten or dim the way a swirl of bacteria carried by wind should. Instead, it can feel almost even, as if someone had turned up a very low light under the whole sea at once. Your ship would seem to glide over one smooth surface of light, rather than through patches of brighter and dimmer water. That evenness is hard to explain if you imagine the glow as nothing more than scattered clumps of tiny organisms bumping into each other in the current. Weather adds one more layer of surprise. Storms usually break things apart in the ocean. Waves crash, water mixes, and anything delicate near the surface gets pulled under or spread thin. Yet, there are accounts of glowing seas surviving through periods of rough weather, the light dimming under the churn, but returning once the water calms. This suggests something about the phenomenon that is more resistant to disturbance than a simple bloom sitting quietly on the surface. Some scientists wonder if the glow's true source lies a little below the surface, protected from the worst of the wave action, only shining up through the water above it. Others argue that the numbers of bacteria involved are so enormous that even heavy mixing cannot dilute them below the point of visible light. Neither view has been confirmed with direct measurements taken during an actual storm passing through a Milky Sea, because so few ships have ever managed to be in the right place with the right instruments at the right time. All of this leaves a picture that resists easy comparison. A glowing field of ocean behaves less like a fire that grows and dies with the wind, and more like something holding a shape according to its own internal rules. Rules no one has fully written down yet. If you drifted across such a field at night, your ship's wake might cut a dark line into the pale light behind you, and yet the light itself would seem to close back up almost as soon as you passed. That gap between the disturbance you cause and the calm the sea returns to is part of what keeps researchers puzzled. The wind blows, the current pulls, the storm passes overhead, and somehow, for reasons still not settled, the glow persists in a shape too steady to be an accident of weather, and too strange so far to be fully explained by anything else. Picture yourself at a desk, covered in old ship logs, each one describing the same strange thing in different centuries and different words. That is close to what a small group of researchers did when they built something called the Milky Seas Project. They gathered reports going back over 400 years from merchant captains and navy officers and whalers, all describing a sea that turned pale and glowed for miles. Reading them side by side, patterns start to appear that no single sailor could have seen alone. You would feel that same quiet shift, the sense of scattered pieces slowly lining up into something with shape. The project's goal was simple to state and hard to do. Researchers wanted to know if these glowing events, called Milky Seas, followed any kind of rhythm. Did they cluster in certain months? Did they favor certain currents, certain temperatures, certain patches of the Indian Ocean, over the Pacific or the Atlantic. To answer that, they needed more than old logs. They needed a way to look at the whole ocean at once, night after night, without waiting for a ship to happen to sail through the right place at the right time. That is where satellites entered the story. Weather satellites carry sensors built to detect faint light at night, originally meant to track moonlight on clouds or the glow of cities. Researchers realized these same instruments might catch something else, the soft, spread-out light of a Milky Sea glowing from below. By searching years of satellite images, they began finding events that no ship had ever reported. Glowing patches sitting quietly in open water, with no witnesses at all. It is a strange thought that the ocean might light itself up for nights on end with nobody there to see it. This connects the glow to something larger than a single strange sea. It ties bioluminescence, that living light made by cold chemistry inside a creature, to the same tools astronomers use to study light from far away. It ties centuries of handwritten logs to modern computers scanning image after image for a pale grey smudge in the black of the open ocean. It ties something as small as a single bacterium to something as large as a patch of sea the size of a small country. Each piece depends on the others, and none of them alone explains the whole thing. One pattern researchers found is that many recorded Milky Seas cluster near the northwestern Indian Ocean, especially in certain seasons. Some scientists wonder if this points to specific ocean conditions there, perhaps warm surface water resting above cooler water below, creating a stable layer where a bloom of light-producing bacteria could grow undisturbed. Other researchers caution that this pattern might simply reflect old shipping routes, ships crossed that stretch of ocean often. So, of course, more sightings came from there. The signal, they say, may be more about where people were looking than about where the glow prefers to happen. The project also raised a harder question about timing. If satellites can catch a glow lasting several nights, does that mean the same bacteria are glowing the whole time? Or does one glowing patch fade while another rises nearby, so it only looks continuous from above? Some researchers lean toward a single sustained bloom, slowly drifting and thinning at its edges. Others think the picture may be closer to a relay, one patch handing off its glow to another before it even fully fades. Both ideas remain open, sitting side by side in the data without a clear winner. What ties all of this together, in the end, is not a finished answer, but a shared question, carried across very different tools and centuries. A sailor's lantern-lit notebook and a satellite's cold electronic sensor are looking at the same unresolved thing from two different distances. A chemist studying the glow of a single bacterium, and an oceanographer studying currents that stretch 1,000 kilometers are, in a strange way, working on the same puzzle from opposite ends. Neither has reached the middle yet. If you stood at the rail of a ship crossing one of these regions tonight, you would have almost no way of knowing you were sailing through data. You would only see the pale glow stretching to the horizon, calm and endless, the kind of light that asks nothing of you. Behind that stillness, though, sits a slow, patient effort to connect small living light to vast moving water. Log entries to satellite pixels, one century to the next. The connections are real. The full picture is still missing pieces, and no one yet knows exactly how many. Long before anyone wrote a scientific paper about glowing seas, sailors carried their own stories about them. If you had walked among the crew of an old trading ship, you might have heard the word Mareel spoken low, almost like a warning. Mareel was an old term for the strange cold fire that sometimes clung to the water. Sailors from Scotland to the Indian Ocean used different words for it, but the feeling behind those words was the same. They were describing something that seemed alive and mysterious, something that did not behave like ordinary water. In many of these old accounts, the glow was treated as an omen. Some sailors believed a glowing sea meant a storm was coming. Others believed it meant the opposite, that calm days lay ahead. There was no agreement because the glow itself gave no clear signal. It simply appeared, sat on the water for a while, and left again without explanation. You can imagine how unsettling that must have felt, watching the sea light up with no cause you could name. Some old stories connected the glow to the presence of the dead, or to spirits thought to move just beneath the surface. This idea fits a pattern found in many cultures. When something in nature glows without fire, without lanterns, without any visible source, people often reach for stories involving spirits or omens. It is a human habit, filling a gap in understanding with meaning that feels emotionally satisfying, even if it cannot be tested. If you stood at the rail of a ship during one of these events, you might understand why those stories took hold. The light has a hush to it, a stillness that feels less like ordinary nature and more like a presence. Not every legend was frightening. Some cultures saw the glow as a sign of good fortune, a blessing on the voyage. Fishermen in certain regions welcomed the glowing water, believing it meant the sea was healthy or full of life. This idea has an odd echo in modern science, since we now know that at least some forms of ocean glow do come from thriving colonies of tiny light-making organisms. The old belief and the modern finding are not the same claim, but they share a strange kind of overlap, and that is worth pausing on for a moment. As sailing technology changed, and ships grew larger, faster, and less dependent on which way the wind blew, the reports of glowing seas did not fade the way many old legends did. They kept showing up in logs written by trained officers, not just old folk tales passed between sailors. This shift mattered. When many separate crews independently write down the same details, the descriptions stop looking like myth and start looking like a real event that needs an explanation. The glow did not change. What changed was who was writing about it, and how carefully. By the time steam-powered ships crossed the same waters, the old superstitions had mostly faded from official reports. Captains still noted the glowing seas, but now they described them in the language of instruments and observation rather than omens. Water temperature, wind direction, the exact shape of the light on the horizon. The wonder did not disappear. It simply moved into a new kind of language, one that tried to measure the mystery instead of interpret it as a message. Even now, the old feeling has not fully gone away. Modern crews who pass through one of these glowing patches sometimes describe the same eerie stillness that sailors wrote about centuries ago. The light spreads without a source you can point to, and the sea looks like it is lit from somewhere inside itself. If you found yourself standing on deck during one of these nights, your body would feel that same old pull, even without believing in omens. Something in us still responds to light but has no clear explanation. What has truly changed then is not the ocean. Bioluminescent bacteria have likely been producing this kind of glow for a very long time, long before any humans stood on a wooden deck to see it. What has changed is our framework for understanding it, moving from spirits and signs toward biology and chemistry. Though even that modern framework still leaves large gaps, we know more about the tiny organisms involved than sailors of the past ever did. We still do not fully know how they organize themselves across such enormous stretches of water, glowing together for days at a time. The legends may have lost their supernatural shape, but the core mystery inside them The question of how the sea can shine on its own remains as open today as it was when the first sailor whispered the word Mareel into the dark. Picture yourself at the bow of a ship, moving through water that has no shadow in it at all. Every other kind of light throws a shape behind whatever blocks it. A lantern makes a shadow. A candle makes a shadow. Even moonlight, thin as it is, still lets a mast or a coiled rope draw a dark line on the deck. The Milky Sea does not work that way. The light comes from below and around and inside the water itself, so there is nothing for a shadow to fall against. If you stood at that rail, your own body would seem to float in a glow that surrounds you completely, with no dark edge to prove you're really there. Ordinary bioluminescence, the kind that flashes when a fish darts through disturbed water, behaves the way light usually behaves. It has a source you can point to. A wave breaks, and a streak of blue-green fire runs along its crest, bright for a second, then gone, leaving the sea dark again until the next disturbance stirs it away. That kind of glow throws real shadows in the sense that it has a clear boundary between lit water and unlit water. You can watch the line move. The Milky Sea erases that line. The light does not flicker in and out with each motion of the ship. It simply exists, low and steady, the same in front of the bow as behind the stern, the same near the hull as far out at the horizon. Sailors who described this glow often reached for the same comparison, across centuries and different languages. They said it looked like sailing over snow, or over a field of milk, or through fog that had somehow caught fire without any heat. The comparison to snow is worth sitting with for a moment. Snow scatters light evenly in every direction, which is why a snowfield under a full moon seems to glow from everywhere at once, with soft edges and no true shadow beneath a person standing in it. Some researchers wonder if the Milky Sea works on a similar principle, with light being produced by countless bacteria spread through the water in numbers so large and so even that the whole volume of the sea near the surface behaves like one glowing surface, rather than a collection of separate points. That explanation covers the visual effect, but leaves the harder question standing. Snow reflects light that already exists. The Milky Sea makes its own. Each bacterium is producing that glow through a chemical reaction, and for the light to look this smooth and this constant, the population producing it would need to be almost perfectly even in its distribution, night after night, for as long as the glow lasts. One idea is that a bloom this large simply averages itself out, the way a crowd of separate voices can blend into one steady hum. A competing idea holds that something is actively keeping the bacteria distributed this way, some property of the water or the way it circulates, though what that something might be remains unclear. The color itself carries a piece of the mystery. Most reports describe the glow as pale blue-white, close to the color of moonlight on cloud, though some describe it as closer to the soft green of old glass. This is not the sharp blue of a single dinoflagellate flashing at the touch of an oar, and it is not the yellow-white of any artificial light a ship might carry. It sits in its own narrow band, produced by a specific chemical process inside the bacteria, one that turns energy into light, without producing heat the way a flame does. If you passed your hand through that water, it would come up cool and wet and faintly luminous, the light clinging to your skin for a moment before fading, with no warmth at all to match the brightness. From a distance, sailors describe the horizon disappearing entirely on nights like this, the line between sea and sky erased because both were the same pale color. Modern satellite images, taken from far above the ocean, confirm the shape and size of these glowing patches, sometimes tens of thousands of square kilometers wide, but they cannot capture what it looks like from the deck, where the glow has no shadow, no source you can point a finger at, and no clear edge where it starts or ends. The instruments can measure the light's brightness and its color and its shape from orbit. They still cannot fully explain why light spread across so much open water behaves as one continuous, shadowless glow instead of scattered flickering points. That gap between what can be measured and what can be understood is where the mystery still lives tonight, quietly, somewhere out on the dark water. If you leaned over the rail of a ship crossing a milky sea, you would notice something odd before your eyes could explain it. The water sounds the same as any other night ocean. There is the soft slap of waves against the hull. There is the low hush of the wake trailing behind the stern. Nothing in the sound tells you that the sea below is glowing. The light and the sound seem to belong to two different oceans, and that gap is part of what makes the mystery so quiet and so strange. Sailors who wrote about milky seas often mentioned this same disconnect. The water looked lit from within, pale and steady, but it made no new noise to match the light. No hum, no crackle, no hiss rose up from the glowing water. Compare that to a breaking wave full of ordinary sparkle, the kind caused by small creatures called dinoflagellates. Those waves often seem louder in memory because the eye and the ear agree that something sudden is happening. In a milky sea, the eye reports a slow event. The ear reports nothing unusual at all. This silence is not really silence, of course. The ocean is full of sound humans cannot easily notice. Waves carry the creak of the hull, the distant call of wind moving across open water, sometimes the far-off song of a whale passing beneath the keel. None of these sounds change when the water turns pale and glowing. If you stood at the rail, the water under your hands would feel exactly as cool and restless as any other sea, even while it poured out light in every direction. Some researchers have wondered whether the organisms responsible for the glow, likely a type of light-making bacteria called Vibrio harvii, might also produce some faint chemical or physical signal beyond light. So far, no instrument has found one. The glow appears to be a purely visual event, a cold chemical light called bioluminescence, made without heat, without vibration, without any sound a human ear could catch. It is light with no accompanying voice. That absence is worth sitting with for a moment, because it means the bacteria are doing something remarkable in complete acoustic silence. There is a second kind of sound worth thinking about here, though, and that is the sound sailors made when they saw a milky sea for the first time. Old logs describe voices dropping low, footsteps slowing, the quiet murmur of a crew standing at the rail instead of going about their work. One captain in the 19th century wrote that his men grew hushed as if walking into a church. This is not a sound the ocean produced, it is a sound the humans produced in response to something they could not explain. In that sense, the true sound of a milky sea might be human, not oceanic. A lowered voice, a held breath, boots moving carefully across a deck lit by water instead of moon. Modern researchers studying the Milky Sea's phenomenon have tried listening underwater with hydrophones, instruments that pick up sound beneath the surface. During the rare moments ships have crossed a glowing patch with the right gear on board. So far, nothing distinct has turned up that separates a glowing patch of ocean from a dark one nearby. The bacteria causing the light are far too small and far too quiet to leave any trace in sound. If there is a hidden acoustic signature to a glow spanning hundreds of kilometers, no one has found it yet. That absence itself is a kind of finding, one more piece of a puzzle that keeps refusing to resolve. It leaves us with a strange picture, a light bright enough to be seen from a satellite in orbit, spread across a stretch of sea larger than some small countries, and yet acoustically indistinguishable from ordinary water. The wind still sounds like wind. The waves still sound like waves. Whatever conversation is happening between billions of bacteria, coordinating their glow across such distance, it happens below the threshold of any sound we know how to hear. Some scientists suspect the coordination might rely on chemical signals passed between individual bacteria, a process called quorum sensing, where enough neighbors trigger a shared response. But chemical signaling, unlike sound, leaves nothing for a hydrophone to catch. If you drifted through a Milky Sea tonight, your ears would tell you almost nothing. Your eyes would tell you everything. The whole event would arrive as sight alone, silent and complete, stretching to every horizon without a single sound to mark its edges. That imbalance between what you see and what you hear may be one of the gentlest mysteries in this story, small and easy to miss, and yet it says something true about how strange this glow really is. Picture a single firefly blinking in a dark field. Its light is small, warm, and brief. Now imagine that same small blink multiplied by more points than you could count in a lifetime, spread across a stretch of sea the size of a small country. That is the strange math at the heart of a Milky Sea. One glowing bacterium is almost nothing. 8 trillion of them, moving together in the same patch of water, become something the human eye reads as a solid field of light. You would feel that scale in your chest before you understood it in your mind, standing at the rail with the whole horizon turned pale. Scientists who study bioluminescence, light made by living things through chemical reactions in their bodies, often reach for other natural comparisons to help explain the numbers. Fireflies blink, one at a time, each insect controlling its own flash. Falling ash from a wildfire drifts down in a loose, uneven scatter, no two flakes landing the same way. Snow falls thick and quiet, covering a field in white, but it falls because gravity pulls it, not because the flakes agree to fall together. A Milky Sea does not behave like any of these. It behaves as if some invisible signal has told an entire population of bacteria to switch on their light at the same time, and to keep it on for days. The bacteria responsible, single-celled organisms far too small to see without a microscope, produce light through a chemical process called bioluminescence. Inside each cell, a molecule reacts with oxygen and releases a small burst of light as a byproduct. One cell's glow is faint enough to miss in daylight, but researchers estimate that in a mature Milky Sea, the concentration of glowing bacteria can reach many thousands per teaspoon of water, spread with strange evenness across the whole bloom. Multiply that density across 100,000 square kilometers of ocean, and the numbers stop feeling like biology and start feeling like something closer to weather, one theory suggests. The bacteria are living on the surface of tiny algae, riding along as the algae bloom and multiply across the sea. If the algae population balloons under the right conditions of warmth, nutrients, and calm water, the bacteria riding along could balloon with them, reaching the density needed to glow as one continuous field rather than a scattered points. This would explain the strange evenness of the light since the bacteria would be distributed the same way the algae are distributed, smooth and wide. But this theory still leaves an open question about timing. Algae blooms can last for weeks. Reported Milky seas usually fade within a handful of days. Something about the glow itself does not match the pace of its supposed source. A competing idea points to nutrient patches drifting up from below. Thin, invisible clouds of chemical fuel rising from the deep ocean into the surface layer. If bacteria happen to be present when one of these patches arrives, they could multiply fast enough to light up a wide area within hours, then dim again once the nutrients are used up. This would explain the sudden appearance and sudden disappearance sailors have described for centuries, but it does not fully explain how the glow stays so uniform over such a large area, since ocean nutrients rarely spread with mathematical evenness. The math of a Milky Sea, in other words, resists both explanations equally. Something makes the light rise together, spread evenly, and fade together, and no single number or ratio yet accounts for all three at once. Researchers who work with satellite images have tried a different kind of math, measuring the size, shape, and duration of glowing patches across many recorded events. Some patches stretch over 100,000 square kilometers, an area larger than some countries, holding their shape for 2 or 3 nights before breaking apart. The consistency of that size range, appearing again and again in old ship logs and modern satellite data alike, suggests some kind of natural limit at work, though no one has identified exactly what sets it. If you sailed into the heart of one of these events, the numbers would stop mattering. You would only feel the pale light pressing evenly against the hull in every direction, with no way to guess how far it reached or how soon it might end. For now, the comparisons to fireflies, ash, and snow remain just that, useful pictures rather than full answers. The real arithmetic behind a Milky Sea, the exact rules that tell a whole sea of bacteria when to glow, when to spread, and when to go dark together, is still being worked out, one dataset at a time. Picture yourself on a ship at night, far from any shipping lane, watching a pale glow spread across the water. You would have no way to tell anyone about it. There is no camera near your bunk, no satellite link waiting for your report. This is the quiet truth behind the Milky Seas. Most of them may pass without a single human witness. The shipping lanes of the world cover only a small share of the ocean's surface. Most cargo routes follow narrow, well-worn paths between major ports. Outside those paths lie enormous stretches of open water where ships rarely go. A glow could spread there for a week and fade again, and the only record would be the plankton themselves, settling back into darkness with no one to ask what happened. Even within shipping lanes, most glows likely go unrecorded. A crew member might notice a strange brightness on the horizon and think little of it, assuming it comes from moonlight through cloud, or the reflection of running lights on calm water. The night sea already holds so many small mysteries. A pale shimmer near the bow might seem like just one more, not something worth writing in a log. You would feel this uncertainty yourself if you stood at the rail during such a night. The glow beneath you would seem enormous, undeniable, impossible to miss. Yet, without a photograph, without a second witness, your own memory becomes the only proof. Sailors who reported Milky Seas in past centuries often faced doubt from people who had never left dry land. Some old logs describing glowing water were quietly set aside by editors who assumed the sailor had been drinking, or dreaming, or exaggerating for a good story. This gap between experience and evidence is part of what has kept the mystery going. Confirmed sightings verified by satellite imagery, most notably from research led by oceanographer Stephen Miller in the early 2000s, gave scientists their first solid proof that these events happen at the scale sailors described. But satellites only capture what happens to be in their path during a clear pass over open ocean at night. Glow that lasts 3 days might occur entirely between satellite passes or under cloud cover and vanish without any image ever recorded. One idea researchers hold is that Milky Seas may be far more common than the handful of confirmed sightings suggest. Under this view, the ocean glows somewhere on Earth many nights each year, but only a small fraction gets caught by a satellite, a ship, or a fisherman with a phone camera at the right moment. A competing view holds that the true events are genuinely rare, tied to specific and uncommon conditions in the water, and that most pale glows people notice at sea come from smaller, shorter bioluminescent sparkle, rather than the sustained Milky Sea glow. Which explanation is closer to the truth remains an open question, since no one has found a reliable way to monitor the whole ocean at once. This fragility matters because it shapes how little scientists can say for certain. Every confirmed sighting is treated almost like a fossil, a rare trace of something that happened and then stopped, leaving behind only faint evidence. Water samples from a glowing patch degrade quickly once brought aboard a ship. The bacteria that may cause the light do not always survive transport back to a lab in a state that lets researchers study them properly. Each missed report, each undocumented glow, is a small loss to the record of a phenomenon that already offers so little to hold on to. If you tried to design a system for catching every Milky Sea as it happens, you would need something like constant satellite coverage, always watching, always capable of separating true bioluminescent glow from moonlight and cloud and haze. No such system exists yet. What we have instead is a patchwork, built from decades of sailors' notebooks, a scattering of satellite images, and a handful of research voyages that happen to be in the right place. The whole picture stays incomplete, held together by chance encounters, rather than steady observation. You would likely never know, standing on a quiet deck at night, whether the glow beneath your feet was one of the rare events that would end up documented, or one of the many that simply comes and goes, unseen by any instrument, unrecorded in any book. The ocean does not seem to need an audience for whatever it is doing down there. It glows, or it does not, on its own schedule, in its own places, for reasons that remain, for now, entirely its own. If you spread every reported Milky Sea across a map of the world, you would not see them scattered evenly. You would see them clustered again and again in certain quiet stretches of ocean, as if the sea itself keeps returning to the same rooms in its house. The Northwest Indian Ocean holds more recorded sightings than almost anywhere else on Earth. The waters near Java, in Indonesia, come next. These are not random dots on a chart. Something about those places seems to invite the glow, and researchers are still trying to say exactly what that something is. One clue lies in the seasons. Many of the sightings near the Arabian Sea and the waters off Somalia happen during certain monsoon months, when winds shift and currents change their pace. A monsoon is a seasonal wind that reverses direction and often brings heavy rain. When it stirs the upper ocean, it can pull nutrients up from below, feeding the tiny plankton that bacteria may later depend on for their own glow. If you stood at the rail during one of these windows, the sea around you might already be gathering the ingredients for a light you would not see for weeks. A second clue lies in the shape of the seafloor and the paths of slow-moving currents. Some of the same regions where Milky Seas appear also sit near upwelling zones, places where cold, nutrient-rich water rises from the deep to the surface. Upwelling can turn a plain patch of ocean into a rich one, thick with the small organisms that other small organisms feed on. It is a tempting pattern, but correlation is not certainty, and plenty of upwelling zones around the world have never once produced a documented glow. The map raises more questions than it answers. There is also the matter of what counts as a sighting at all. For centuries, records depended entirely on which ships happened to be crossing that stretch of water at that moment, and whether their captains thought the glow was worth writing down. A busy shipping lane will generate more reports than an empty one, even if the empty one glows just as often. This means the map of Milky Seas may partly be a map of where ships travel, layered awkwardly over a map of where the ocean actually glows. Untangling the two remains one of the harder problems in this field. Modern satellite data has helped, because satellites do not care whether anyone is watching. Instruments in orbit have caught the pale glow of Milky Seas over open water, far from any shipping route, in stretches of ocean no vessel happened to be crossing. These sightings confirm that the phenomenon is not only a trick of busy trade lanes, they also hint that some events may be larger or more frequent than the historical logs ever suggested. The true number of Milky Seas each year could be far higher than recorded history implies, simply because most of the ocean has no witnesses at all. Even within the known hotspots, no one has found a reliable way to predict exactly when a glow will begin or where its edges will fall. Two ships crossing the same waters a week apart might report entirely different nights, one calm and dark, one lit from below in every direction. The bacteria responsible seem to need a very particular mix of nutrients, temperature, and existing plankton blooms to reach the numbers required for a visible glow. Get one factor slightly wrong, and the sea stays ordinary. Get them all right, and it turns pale for days. Some researchers wonder whether certain seafloor features, still poorly mapped in these remote regions, play a quiet role in shaping where nutrients gather. Others think the pattern has more to do with large, slow ocean currents, carrying blooms from one place to another. So the light we see is really the tail end of something that started somewhere else entirely, out of sight. Neither idea has been confirmed. Both remain open, sitting side by side in the notebooks of people who study this. What is agreed upon is smaller than what is still uncertain. The ocean seems to have favorite places to glow, shaped by wind, water, and life working together in ways not yet fully mapped. If you sailed into one of these named regions on the right week, in the right year, the water beneath your hull might already be preparing to shine, following a rhythm still being learned by the people who study it, one recorded night at a time. Picture yourself floating far from any ship, far from any satellite, above a stretch of open sea that no one is watching tonight. The glow could be there right now, spreading quietly under a sky with no witnesses. If it is, it will pass unrecorded. No logbook will hold it. No orbiting camera will happen to pass overhead at the right hour. The ocean does not seem to need an audience to do what it does. This raises a question that sailors and scientists alike have circled for years. How much of this glowing is happening right now, in places no one will ever see? The known events, the ones written into logs or caught by satellites, may be a small fraction of a much larger pattern. Most of the deep sea is never observed at all. A glow could rise and fade 1,000 times over, in waters no ship crosses and no lens records. Some researchers wonder if the visible cases, rare as they are, only mark the edges of something more common underneath the surface of routine. The bacteria responsible for the glow live throughout much of the ocean, not just in the handful of places where a Milky Sea has been reported. If the right combination of nutrients, temperature, and stillness can happen in one patch of the Arabian Sea or the waters near Java, there is no clear reason it could not happen elsewhere, unnoticed, on a night with no vessel nearby to feel the light against the hull. Others argue the visible cases are genuinely rare, tied to specific currents and specific plankton blooms that only build in a few corners of the world. In this view, the glow is not hiding everywhere, waiting for eyes. It is something the ocean does sparingly, shaped by conditions that come together only now and then, in only a few places. Both views agree on one point. The instruments used to search for glowing water today are still limited by clouds, by moonlight, by the narrow path the satellite happens to fly. A glow could exist and simply miss every window humans have built to catch it. If you drifted above such a patch, blind to it in the dark, your body would feel nothing different at all. The water would hold you the same way it always does, cool and steady, rising and falling with a slow rhythm. There would be no signal reaching your skin, no warmth, no sound. The light, if it were there, would be happening entirely without you, a private glow, with no need for a witness to make it real. Some scientists have begun using ocean color sensors that log data continuously, hoping to catch a glow mid-event rather than stumbling on it after the fact in old satellite archives. Even so, gaps remain. Storm systems can hide a glow under cloud cover for days. A glow could bloom and fade completely within that blind window, leaving no trace behind except perhaps a change in the water's chemistry that no one thought to sample in time. The ocean, in this sense, keeps its own secrets simply by being too large and too far from constant watching. There is a quieter possibility too, one that some researchers raise without much fanfare. Maybe not every glow is meant to be a bright, continuous field, bright enough for a camera far above to register. Maybe some glows are smaller, dimmer, present only in patches too faint to register against moonlight or haze. If that is true, the known cases of Milky Seas might represent only the brightest, largest examples of something that happens in gentler, smaller ways far more often, hidden simply because they never cross the threshold that makes them visible from space. None of this resolves the deeper puzzle. It only widens it. If the glow can appear in places no one watches, then understanding why it happens at all becomes even harder, because the full range of cases stays out of reach. Scientists can only study what they manage to catch, and the ocean is not obligated to perform for the instruments pointed at it. The rest, for now, stays in the dark, quite literally, somewhere beneath waves that no one happens to be crossing. If you were there, in that unwitnessed place, the sea beneath you would not know or care whether anyone noticed. It would simply be doing what it does, glowing or not glowing, according to rules not yet written down by anyone watching from a deck or a satellite. The vastness of the ocean guarantees that some part of this mystery will always remain outside the reach of human eyes, waiting in the dark for no one at all. If you could gather every instrument built in the last 50 years and point them all at a Milky Sea, you would still walk away with questions. Satellites can measure the glow's shape and size from far above the clouds. Ships can carry water samples to a lab and count bacteria under glass. Sensors can record the exact wavelength of light coming off the waves. And yet none of these tools working together can fully explain how the glow starts, how it holds its shape for days, or why it ends when it does. You would feel that gap yourself, standing at the rail, watching a light with no clear cause spread out farther than your eyes can follow. Modern satellites have given researchers something sailors never had: a view from above. Low-light sensors in orbit can pick out a Milky Sea glowing among the black water around it, sometimes marking a patch of light larger than a small country. This has settled one old argument. The glow is real, and it is large, and it is not a trick of tired eyes on a rolling deck. But settling that question only opened a harder one. Seeing the shape of a glow from space does not explain why the bacteria inside it decided to light up together in the first place. Laboratory work has filled in some of the chemistry. Researchers know that certain marine bacteria, too small to see alone, carry genes that let them produce light through a chemical reaction. They know this glow tends to switch on only when the bacteria reach a certain crowd size, a process called quorum sensing, where enough microbes packed together seem to trigger the whole group into glowing as one. This explains how a single colony might light up. It does not explain how that behavior could spread evenly across a stretch of ocean the size of a small sea, staying lit for a week or more, as if every bacterium involved were following the same unspoken signal. One idea, still just an idea, is that the bacteria may be living inside or on the surface of tiny drifting algae, and that a bloom of that algae could carry the glow wherever the current takes it, like a lantern with a very large, very slow wick. Another possibility points to deeper water rising up from below, called upwelling, that might carry nutrients and bacteria to the surface all at once across a broad front. Neither idea has been confirmed well enough to close the question. Researchers who study these events tend to speak carefully, using words like may and one possibility, because the data collected so far cannot rule out other explanations. Part of the trouble is timing. Milky Seas do not wait for research ships to arrive. They form somewhere in the vast stretch of ocean, glow for a matter of days, then fade before anyone with the right equipment can reach the spot. A handful of ships have sailed directly through one and taken samples. That has given science its best direct evidence. But a handful of samples cannot describe an event that may unfold differently every single time it happens. You would feel that same shortage of certainty if you tried to hold water from a glowing sea in your hands. It looks the same as any other seawater once it is out of the dark. There is also the matter of scale itself, which remains hard to hold in the mind. A single bacterium glowing is easy to picture, a small blue-white point in the dark. A sea glowing from horizon to horizon for days is something else entirely, made of uncountable trillions of those same small points, acting in a kind of unison. No one has fully mapped. Some researchers wonder if we are looking at ordinary biology, simply working at a scale we rarely get to observe. Others wonder if there is some organizing force in the process, still waiting to be described, something about how these bacteria communicate or spread that current models do not yet capture. None of this makes the ocean seem less real or less physical. Every part of the glow, from the chemistry in a single cell to the drift of a current, follows laws of nature that hold true everywhere. The atoms making that light are the same atoms in your own body, formed long ago in stars, carried through the sea, and shaped now into something that quietly lights the water at night. What remains unexplained is not whether this is natural. It is how something built from parts so small, can, now and then, act together on a scale that reaches the horizon. If you stood at the rail of a ship crossing that glow tonight, the mystery would still be sitting there, patient and unresolved, waiting for someone with a longer notebook than ours. Somewhere on the ocean tonight, the water might be glowing. You will never know exactly where, and neither will the satellites that sometimes catch it by chance, sweeping their slow orbits over a dark sea that has decided, for reasons still hidden, to shine. If you were there, standing at some ship's rail with the engine humming under your feet, you would see no edge to the light. It would stretch to the horizon, and past it, pale and even, like a field of snow lit from below. We have walked through many pieces of this mystery together tonight, the old sailors who wrote of milk seas and were not believed. The tiny bacteria, each one far too small to see, that somehow act as if they belong to something larger than themselves. Satellites that photograph patches of glowing ocean, the size of small countries, holding steady for days, defying the currents and winds that should have torn any single bloom apart. We have looked at the chemistry of cold light, the quiet argument between researchers who favor bacteria and those who wonder if something else moves through that water too. None of it resolves. All of it stays open, soft-edged, unfinished, like the light itself. That is, in its way, a comfort. Not every question needs an answer to be worth holding. The glowing sea has been doing this, by all evidence, for as long as sailors have kept logs, and probably long before anyone was there to write anything down at all. It does not perform for us. It does not wait for instruments or explanations. It simply happens, out past the reach of most coastlines, in stretches of water so far from land that only a handful of ships ever cross them. Somewhere out there right now, the same pale light may be spreading across the surface of the sea, with no one watching at all. Picture it one more time, gently, before you let it go, a ship's wake, cutting through water that shines instead of splashing. The stars faint overhead, because the sea below is competing with them for your eyes. A sailor at the rail, feeling small and strangely calm, wrapped in a light that asks nothing of them and explains nothing to them either. That image can be yours now too, even from your bed, even with your eyes closed. You do not need to be on the water to hold it. You only need to imagine the hush of it, the wide, pale stretch of it, the sense of something ancient and alive, quietly doing what it has always done. Far from any shore, the world is full of these unresolved corners, places where life and light and water meet in ways our best explanations still cannot fully hold. That should not trouble you. It should settle you, the way it settles the ship's wake, the way it settles into the dark water and disappears again to ordinary black once the bloom has run its course. Mysteries like this, one, are not gaps in the world. They are part of its shade. The ocean does not need us to understand it in order to keep glowing, and you do not need to understand everything in order to rest. So let the glow fade now, slow and gentle, the way it must fade somewhere out on the real ocean tonight, thinning at its edges, sinking back into darkness, leaving only calm black water and a sky full of quiet stars. Let your own thoughts do the same. Let them stretch out flat and pale for a moment, then dim, then go soft, then go still. Somewhere far from any coast, the sea may still be shining without anyone there to see it. You do not have to solve that. You only have to know that it is possible, and let that possibility hold you the way water holds a ship, gently, without effort, all through the night, we may learn more about the glowing sea before long. New satellites, new sensors, new ships willing to sail into a patch of light instead of around it, or the mystery may stay exactly this open for a long time yet. One more soft unanswered question drifting on a very old, very patient ocean. Either way, for tonight it is enough to picture it, enough to let the pale light spread once more behind your closed eyes, wide and quiet and endless, and to feel yourself floating gently on top of it, safe, unhurried, and slowly, slowly falling asleep. Subscribe for a brand new Earth topic every night. One tap, and something wonderful is waiting for you tomorrow. Sweet dreams.